All right, so 2.7, we're going to talk about the spread of data. So how far apart the data gets spread. So this one we're going to talk about with the standard deviation. It's the number that measures how far the values are away from the mean. Okay, so the standard deviation is how far away the data is from the mean. Right? And the standard deviation provides a numerical measure of the overall amount of variation and can be used to determine whether a particular data set value is close or far away from the mean. So it's telling you how far away it is from the mean. So the standard deviation is used to determine whether a data value is close or far away from the mean. So we're going to go through this scenario. Suppose that Rosa and Bin both shop at a supermarket A. Rosa waits at the checkout counter for 7 minutes, and Bin only has to wait for 1 minute. At the supermarket A, the mean waiting time is 5 minutes. So the mean is 5 minutes, and then the standard deviation is 2 minutes. Okay? So Rosa waits for 7 minutes. So 7 is 2 minutes longer than the average time. And with it being 2 minutes longer than the average time, we know that one standard deviation is 2 minutes. So Rosa's waiting time is one standard deviation above the mean or above the average. Okay, now Bin only had to wait 1 minute. Okay, 1 minute is 4 minutes less than the mean 5. So 4 minutes, remember each standard deviation is equal to 2 minutes. So 4 minutes means that he is 2 standard deviations below the mean. So 2 standard deviations below the mean. So let's say that Mr. Shah went to the same grocery store and he had to wait 7 minutes. He would be like Rosa, waiting 7 minutes, and he would have 1 standard deviation above the mean. Now let's say that Mrs. Whatcott went to the same supermarket and she only had to wait 2 minutes. So if she only had to wait 2 minutes, that's 3 minutes less. So if one standard deviation is 2 minutes, she had 3 minutes less, so she would be 1.5 standard deviations below the mean. All right, so we have specific symbols that we use to talk about standard deviation when it comes from whether the sample or from the population. So we use lowercase s to come when the standard deviation is from the sample, and we use lowercase sigma to represent that the standard deviation is from the population. So remember that we said that x bar is the mean from the sample, s is the standard deviation from the sample, and mu is the mean from the population, and sigma is the standard deviation from the population. All right, so a deviation is how far something is away from its mean, from that data set. And we're not going to have to do a lot of this, but you need to understand that variance is the average of the squares of the deviations. So if we take all the deviations, or how far all of the data values are away from the mean, and we square those and take the average, that's our variance. Now, Snow does have a tendency to ask a question about this, so I'm going to just simplify it down here. Let me slide this down. That the standard deviation for the sample is the square root of the variance. And it doesn't matter if this is from the sample or from the population. It is the square root of the variance. Don't worry too much about all of this, okay? Just remember that the standard deviation is the square root of the variance. This is how you do it longhand, okay? So if we say for this data set, our mean is 10.525, you take each data point and you see how far away it is away from the mean. In other words, you're figuring out the deviation. And then you figure out the deviation for all of these, and then we square that deviation. And then we take the frequency to figure out how many there are, because this one only had 1, so you only had to multiply it by 1, but this one had 6, so we need to multiply it by 6. Then you take all of these, and that is the sum of the squares of these deviations. This is your variance, okay? So our the sample variance is the same as your s squared, Okay, remember, because S was the square root of variance, so variance is S squared. So if this is our variance, to find the standard deviation, we'd have to take the square root of that variation. So if this is the total, then we need to figure out, so this is the sum of all of the squares of the variance, we need to figure out the average of that. So we divide that by the number 20 minus 1, and that will give us our variance. Then we square root that, and that tells us our standard deviation. This is how we did it old school. Okay, now you have calculators that we just put that in there, and it's going to tell you when you do your number summary what your standard deviation is. So you need to understand where those come from, but more than that, you need to be focused on what the standard deviation tells us about the data. Because you're going to have technology that's going to help you calculate what that standard deviation is, but you're going to have to interpret what that standard deviation means. Okay. And one thing to remember, if we have a symmetrical distribution, like you talked about in Math 3, where you focused on normal distributions, those were symmetrical, the standard deviation is very helpful. But if you have a skewed distribution, it might be better to look at your first quartile, median, third quartile, and your smallest and largest values to get a better idea of what the data is actually telling you. All right, so let's say that we're wanting to compare values from different data sets. Standard deviations can be helpful, but we have to convert them to something called a z-score so that we can compare data values that are coming from different data sets. All right, so this z-score, we use the data value and subtract the mean divided by the standard deviation of that data set. That gives us the z-score. Now, whether it's coming from a sample or population just means that you're going to use the mean and standard deviation from the sample or the mean and the standard deviation from the population. But you have to convert these to z-scores before you can actually compare them to each other because we're getting them from different data sets. All right, so example 2.35, we have two students, John and Allie, from different high schools. We want to compare or figure out who has the highest GPA, but this is when they're compared to their school. Okay, which student had the highest GPA? So we have the GPA of John, which is 2.85, and the school mean is 3.0. The school standard deviation is 0.7. And for Allie, they calculate at her school, they calculate GPA a little bit differently. She has a GPA of 77, and the school mean GPA is 80, and the standard deviation is 10. So what we do is you take their raw score and subtract it from the mean. So subtract the mean from that, and then divide by its standard deviation. So now the z-score for John is negative 0.21. And then we have for Allie, her score, or her GPA of 77, subtracting the mean of the school, which is 80, divided by its standard deviation, 10, gives her a z-score of negative 0.3. All right, so now that we've converted them both to z-scores, we can actually compare them, and that comparison will have meaning. So when we look at John's, we can say that his 0.21 standard deviations below the mean is better than Allie's 0.3 standard deviations below the means. So if we take a look at these, the reason we say that this one is better is because generally saying you want to have a higher GPA. So you always have to put it back in context when you're comparing things to see if it's good or bad or to make any kind of evaluation about it. So once again, in order to compare information from two different data sets, you need to convert them to z-scores, and then you can compare the z-scores.